Our last two polar curves begins with a lemniscate. All right. Now, what's a lemniscate? Well, it's of the form r squared is a constant a times cosine 2 theta or sine 2 theta. All right, this is always just 2 theta, and on the left-hand side, it's not r anymore, it's r squared, so it's easy to recognize. Since r is squared, then for each acceptable angle of theta, that is where the right-hand side has a positive value, r is going to come up with two values, both positive and negative. So what that means is we actually trace out two parts of the curve at once. Okay, in other words, r is plus or minus the square root of 4 sine 2 theta. 4 sine 2 theta must be greater than or equal to 0 for that to make sense at all. But for each value of theta, we end up with two values of r. Right? Again, what am I going to look at? Angles where a sine is largest, smallest, and 0. Right? But I set the angle 2 theta equal to that. So 0, pi halves pi. Theta then is half of each. 0, pi over 4, pi over 2. And so these are the points. When theta is 0, r is 0, so I'm at the origin. When theta is pi over 4, then it's the sine of pi halves, which is 1, right? Which means r squared is 4, r is plus or minus 2. And when theta is pi halves, it's the sine of pi. I'm back to 0 again, right? So how does it go? I start at 0, and then I trace this way. I also, by the way, trace this way because r is either plus or minus. So that at the point 2, 4, the polar point 2, 4, I'm there. And down here at minus 2 pi over 4. And then I go back to the origin again, right? Each value of theta, again, gives me two values of r, one positive and one negative. Now I'd like to point out, I call a lemniscate a bow tie. Do you see why? Do you get it? Because that's what it looks like. And again, if you replace sine with cosine, what happens is this gets rotated. The picture gets rotated. All right, the last set of curves I'm going to look at are spirals, where r really isn't a trig function, but it's equal to like a theta or e to the theta. Now, if it's e to the theta, then I know e to the theta is strictly greater than 0. So if a is greater than 0, I don't have to worry about negative r's, right? So let's plot those. They're called spirals. You'll see why. What if r is theta, right? So when theta is 0, r is 0, pi halves, pi, pi, 2 pi, 2 pi. Get it? All right, here's 0, 0. Here's pi halves, pi halves. The angle is pi halves, and so is the radius. Remember, pi halves is a number, positive number, 3.14 garbage divided by 2. And then pi, I'm over here. The angle is pi. The radius keeps increasing. That's the point. The radius just keeps increasing. And it spirals out. Now that is for positive theta. If I were to look at negative theta, okay, then r is negative as well. And remember, I have that reflection thing happening. So here is 0, 0, minus pi halves, well, minus pi halves would be down here somewhere. But since the radius is also negative, that's how it gets reflected, right? So here it is for positive theta, and here it is for negative theta. And if you were to superimpose both of those graphs on the same one, okay, then this would be like going out like this and around like that. And that would be a total picture of r is equal to theta. All right, so those are spirals. Leminscates, remember, I call bow ties. And that's all I have to say about classic polar curves.